The last portion of Lecture 2 has to deal with significant figures and dimensional analysis. So how do we take those measurements? For example, if I was trying to measure 100 milliliters of water, I may not get the same measurement using those three different devices, using the beaker, using an Erlenmeyer flask, or a graduated cylinder. Each of them come with different error associated with that measurement that depends on the markings available. And we're going to take a look at where significant figures come from and why they are important. So here's an example. Let's measure this steel rod. Well, we'd all look at that and we would say that looking at that steel rod, it is definitely beyond the 9 centimeter hash mark, and it's definitely beyond the 9.1 hash mark. So we would all look at that and agree that it's greater than 9.1 and less than 9.2. So somewhere between 9.1 and 9.2. So all reasonable answers, you could say, I think that's exactly 9.10 centimeters, or I think that's 9.11, or 9.12, or 9.15, right? All of those are reasonable answers because it's beyond 9.1, it's less than 9.2. And none of those would be wrong. And this is where significant figures come in because, as you'll notice, we all agree on the first two numbers, the 9 and the 1. Where we disagree is on the second decimal place, 9.10, 9.11, 9.12, 9.13, or 4, or 5. We'll notice that that last number reported, that's where we disagree, right? I could take a room of 100 people and ask them to measure this, and they would come up with possibly, right, many different answers, all based on how they interpret where that rod stops with respect to the ruler. And that's where our significant figures come in. So significant figures, all that they do is they tell us where is there uncertainty in that measurement, right? So it depends on the instrument being used. Significant figures, they depend on the instrument being used. So significant figures come into play because they are the last number we can report. That's the number where the uncertainty lies with our measurement. So the last number reported, the number where uncertainty lies. Right? Where our interpretation, basically where this comes from is, it's where we have discrepancies in our interpretation of the measurement. And again, that also depends on the instrument being used. Where our interpretation of the instrument and the measurement varies. So for example, we can go 1 decimal place beyond what we can measure. We can measure for sure 9.1 because it's definitely beyond the 9.1 hash mark. We can make one more measurement, and that measurement is where we're guessing, and that's the measurement where the uncertainty lies because we're making a guess. Is that 9.10 or 9.11 or 9.12, 9.13, right? All of those are fine. And here is where we have uncertainty because we are guessing at that second decimal place. We can go, that's fine. We can make that measurement 9.11, 9.12, because we're allowed to go 1 decimal place beyond what we can measure. We're allowed to go 1 place beyond what we can measure. And that is the last number we can report, right? What you cannot say, you can't say, so all of those numbers above are fine. What would be wrong would be to say, oh, this is 9.104756 centimeters. No, that we cannot make that measurement, right? We have no idea what those numbers are. So we cannot go beyond 2 decimal places in this measurement because we're limited by the measuring stick that we have. So here's a question for you, right? These 2 different rulers, and it also exemplifies the difference in the instrument that you're using. Both of these rulers are a meter long. One of them has markings every 5 centimeters, and one of them has a marking every centimeter. So what is the length in centimeters of the red line using ruler A, and then what is the length of the red line using ruler B? So for ruler A, we might look and say, okay, well, that's 25, and maybe that's 27 and a half. I'm halfway between 25 and 30, so maybe this is, we'll say it's just beyond that, so maybe we'll call this 28 centimeters. That's a fine measure. That's a fine measurement because we only have markings every 5 centimeters. For the next one, we have markings every centimeter. So I can go and I can say, okay, here's 25, 26, 27, 28. And if I look across, maybe I'm just beyond that. So I could say I have 28.1 centimeters. We can say that measurement because we have a marking every centimeter, so we can go 1 decimal place beyond that. So here's an example where the instrument you're using changes, right? It changes the measurement you can make. You could imagine if I only had markings every 1 meter and I tried to measure this, right, it would be quite a guess as to the distance. I might say 0.3 meters or 30 centimeters. To determine the number of significant figures, right, there's a couple rules that we have to use. And so basically, all non-zero numbers, if I'm going to report a number, I'm reporting those numbers because I can measure those numbers. So all non-zero numbers are significant. So in this example here, I would have 4 significant figures, abbreviated sig figs. If I have a 0 between non-zero numbers, that is also significant. So I would have 5 significant figures here. Preceding zeros or leading zeros, zeros before a non-zero are not significant. They are placeholders. So in looking at this measurement of 0.00123, I would only have 3 significant figures. Zeros to the right of a decimal place, however, those are significant. Those are significant, right? So in this case, I'm only saying I have 123.000 because I can measure exactly 123.000. If I could only measure 123 and the number ended there, that would be 3 significant figures. But because I can measure beyond that, I can measure 3 decimal places beyond that, this would have 6 significant figures. And another one that comes up is, I should have written in here, are trailing zeros. Are not significant unless a decimal place is used. And so, for example, if I said I had an 800-pound bear and I wrote that as such, that would be 1 significant figure. Because without that decimal place there, This could be 810, 815, it could be 795. These trailing zeros without the decimal place, you're putting those there because you do not know. You're just saying this is very close to 800. It could be less than, it could be greater than, I'm not exactly sure. So 800 written as such is different than 800.0. This means I can measure that I have 800 pounds exactly all the way to the 10th of a pound, right? Here, I'm estimating. Here, right, I'm estimating. So with that decimal place there, you're indicating that you have 4 significant figures and you can measure this exactly all the way down to the 10th of a pound. One way to help us with significant figures is by writing things in scientific notation. In scientific notation, you only report significant figures. So for example, a 747 airplane weighs 183,000 kilograms. How many significant figures in this measurement? It depends on how you write that. It could be 3, it could be 4, 5, 6 significant figures. So by putting that in scientific notation, right, in scientific notation, we only report a number if it is significant. So if I wanted to represent the weight of that plane in scientific notation to 3 significant figures, I would say I had 1.83 times 10 to the 5, or 1.83 e to the 5 kilograms. Both of those would be 3 sig figs. However, if I knew that weight to 4 significant figures, well, then I would say I had 1.830 times 10 to the 5 kilograms, or e to the 5 kilograms, right? That would be 4 significant figures. So by using scientific notation, we make our lives a little bit easier because we only include a number if it is significant. We have a few rules to use when we're doing calculations with significant figures, and they apply to multiplication and division and addition and subtraction. So when we are multiplying and dividing measured numbers, we want to report the answer to the correct number of significant figures, and that's going to be determined by what number in our calculation has the least amount of significant figures. So in a multiplication or a division example, we want to determine, after we do our calculation or our division, we want to look and see how many significant figures we have in each of the numbers. The number with the fewest significant figures will limit how many figures I report in my final answer. When I'm doing addition or subtraction, we want to look at those numbers and look at the decimal places. The number with the fewest decimal places will determine how many decimal places I report in my final answer. So those rules are a little bit different, but they're going to be used for either multiplying and dividing. We're going to use the number with the least amount of significant figures. Addition and subtraction, the number with the fewest decimal places. They'll be used when we report our final answer. So here's just an example with addition. We'll make up some numbers. 28.121, 12.23, 14.11232, and 11.21157. And we'll add all those numbers up and we get a 9. That's 8. There's 4. And 7, 6. And then this becomes 6, 5. So addition and subtraction, we want to look at the number with the fewest decimal places. And so we look over here and we see that I only have 2 decimal places in 12.23. So I should report my final answer to 2 decimal places. So I really should report this as 65.67 will be my final answer for this. I should report this to 2 decimal places. And the reason being that in addition and subtraction, right? In this case, I do not know what is out here, right? By saying 12.23, I'm guessing at the 3. I don't know what number is next in that measurement. Is it a 5? Is it a 7? Is it a 9? And because I'm unsure of anything beyond that second decimal place in the 12.23, that uncertainty carries over when I add things together. And so that means I'm really unsure about anything beyond the second decimal place in the final answer because I was unsure about anything beyond the second decimal place in that second measurement, the 12.23. So in addition and subtraction, we're going to look at what number has the fewest number of decimal places, and we're going to use that when we report our final answer. Again, I would go through the calculation first, and then after you get the calculation, then think about how many significant figures should I report. We're going to do an example with multiplication a little bit later. The last little bit to look at with significant figures is rounding, right? Hopefully we're all familiar with rounding. If we're going to look at, I want to report this to 3 significant figures. 1.2151. I'm going to report that to 3 significant figures. So that means I'm going to drop everything beyond the 1. Well, that number is greater than 5, so that means I would round that up. So to report that to 3 significant figures, I would say 1.22. If it is less than 5, right, then we do not round. We just drop all of those numbers. So here's my second measurement, 1.2143. Again, I'm going to report that to 3 significant figures. I'm going to drop everything beyond the third number. That number is less than 5, so I would just report this as 1.21. The last little bit is dimensional analysis, and we're going to do a calculation example with multiplication that'll help with significant figures as well. And so dimensional analysis is really there just to help you with our calculations in chemistry, just help you with any calculation, any problem solving. And what I think of dimensional analysis is basically we have a number that we're starting with, we have a unit that we're starting with, and I'm asked to find this final answer in a different unit. Well, we need to use a conversion unit and a conversion factor to find this number. So an example that I would think about is how do we get those units to cancel out? That's what dimensional analysis is, a way of just putting out the units that we're using with a conversion factor that would allow us to convert from one unit that we start with to the unit that we're looking for. And so here's the unit that I start the problem with, and here's the unit I'm looking for. Well, I want to use a conversion factor that lets me convert between those 2 units. And as you see, when we do the multiplication, right, that given unit cancels out, and I would be left with my final answer in the desired unit. So here's an example of dimensional analysis. We're driving a car 45 miles an hour. How many feet per second are we moving? And so I would start with, right, I have 45 miles per hour. And I want to multiply by something, right, that eventually gives me a final answer in how many feet per second would I be moving. So I need to do a few things. I need to convert from miles to feet. I need to convert from hours to seconds. And so we can do this. We can either convert miles first or we can convert hours first. You're going to get the same answer, but we can do this using dimensional analysis, right? So I'm going to start off. I've got 45 miles in 1 hour, and I know that, right, I want to multiply by something that takes me from miles into feet. So I'm looking for a final answer of feet, for right now, feet per hour. So I need to have miles down here. So in 1 mile, and then what conversion factor would I use? Well, in 1 mile, I know I have 5,280 feet. So when we go and we multiply, right, miles cancels out, and I have approximately 237,600 feet per hour that I'd be traveling. And let's not worry about significant figures until we get to the final answer. So step 2, now I want to convert feet per hour from feet per second. So I've got 237,600 feet in 1 hour. Well, now I want to multiply by something that takes me from hours to seconds. So I know in 1 hour, I have 60 minutes, and ultimately I need to be in seconds. Well, in 1 minute, I have 60 seconds. So my first conversion will get rid of hours, my next one will get rid of minutes, and my final answer, I'll be left with approximately 66 feet per second. Dividing 237,000 by 60 twice, hours cancel out, minutes cancels out, and I'm left with my desired units of feet per second. For significant figures, we measured that we're moving 45 miles an hour. There's 2 significant figures in that measurement, and that's the fewest significant figures on any number we have here. So I should report the final answer, right? Multiplication and division. We want to report the answer to the number of significant figures of our least significant measurement. So 45 has 2 significant figures. I should report this answer to 2 significant figures. Right, this is an exact number, so that has no influence on my significant figures, and these are exact numbers as well, right? An hour is exactly 60 minutes, and a minute is exactly 60 seconds. So this is just an example of dimensional analysis. How can we set up these problems so we can track units, we can follow units, and know and think about what conversion do I know that would allow me to convert from miles to feet, or seconds to hours or minutes. We can also use this dimensional analysis with the metric system when we're doing conversions between measurements. So for example, I have 10 seconds, and I want to know how many milliseconds that is. I can do the same thing. I know that I have 10 seconds, and if it helps, you can just put that over 1. I want to convert 10 seconds. I want to multiply by something that gives me an answer in milliseconds. Well, if I go and look, my base unit, right, would be right here, and milli is 10 to the minus 3, right? So that means that in 1 second, I would have 1,000 milliseconds. So I multiply, seconds cancel out, I would have 10,000 milliseconds in 1 second. We could do that conversion another way. I could say 10 seconds. I could say that in 1 millisecond, right, 1 millisecond is 1 times 10 to the minus 3 seconds. And I would get the same answer that 10 seconds are 10,000 milliseconds. But again, we can do that with dimensional analysis that allows us to track the units, make sure the units are canceling out properly, and we're using the correct conversion factor to go between our initial measurement and our desired answer. Another example, I've got 1.5 grams. I want to find out how many nanograms that is, right? So I can put that over 1. Well, by looking here, nano is 1 times 10 to the minus 9. So that means in 1 gram, I have a billion nanograms, or that 1 nanogram would be 1/1,000,000th of a gram. So 1 gram would be 1 times 10 to the 9th nanograms. Grams cancel out, and my measurement would be, right, 1.5 grams would be 1.5 times 10 to the 9 nanograms. I could do that conversion the same way I did over here, where I just do the inverse of that, and I would get the same answer. So we can use dimensional analysis in the metric system as well. I would pick, right, both of these are correct. I would pick one way and stick with that one way throughout the semester, and always be thinking when you're doing these conversions, which one is the larger number, right? Grams are larger than nanograms, so that means I need to have many more nanograms, right, in 1 gram to represent that sample. So this would be the correct relationship for that conversion factor. So here's one example for you guys. Platinum has a density of 21.4 grams per cubic centimeter. What's the mass of a platinum bar that's 28 centimeters long, 22 centimeters wide, and 5 centimeters thick? About the size of a textbook. And second part of this question, if platinum is $29.59 per gram, how much would that bar be worth? So here's one for you to try. Step 1, we want to find what's the volume of this. So volume, length times width times height. So 28 centimeters, 22 centimeters times 5 centimeters. So our volume, centimeters times centimeters times centimeters, gives me centimeters cubed. And again, I would not worry about significant figures until we get to the final answer. So don't worry about it. Step 1. Step 2. I have my volume. I need to now convert that volume into a mass using the density. So I've got 3,080 cubic centimeters, right, per 1 silver bar. I need to multiply that by something that gives me a final answer in, right, I want to find out how many grams, right, this bar weighs. So using the density, that's my conversion factor. That's going to allow me to go from volume into mass. And I want volume to cancel out, so my density tells me that I have 21.4 grams, right, per 1 cubic centimeter. So cubic centimeters would cancel out, and that would give me a final answer of approximately 65,912 grams. All right, now that we have the final answer, now we can report the correct number of significant figures. So this is a defined amount, right? I've defined silver as having this density, so that doesn't have a role in our significant figures. However, these are measured amounts, and fortunately for us, I have 2 significant figures, 2 significant figures, 2 significant figures, so I want to use 2 significant figures in our final answer. So I want to report our final answer to 2 significant figures, which means I need to drop everything after the 5. Well, 9 is greater than 5, so I need to round that up. So I would report the final answer as 6.6 e to the 4th, right, grams per bar, or 6.6 times 10 to the 4th grams per bar. That would be the correct answer to 2 significant figures. The next calculation, how much is this bar worth? We can do the same thing with dimensional analysis. And again, let's just use the full number, the unrounded number, before we come to a final answer, and then we can round it and report it accordingly. So if I have something, a bar that weighs 65,912 grams, I want to find out how much is that bar worth. So I need to multiply that by something that gives me the final answer, right? I want to know that final answer in dollars. So I have 1 bar, and I know that that bar is, right here's my conversion factor. That bar is $29.59 per 1 gram. I multiply, grams cancel out, and that's going to leave me how much that bar is worth, right? The value of that per bar. So I multiply, and I should come up with an answer of approximately 1 $1,950,336. Again, I want to report this to two significant figures. So to two significant figures, right, I'm going to report those two. And then the third significant figure is a 5, so that's I'm going to round that up. So I would report this as approximately, that bar would be worth about $2 million. So 2.0 times 10 to the 6, or 2.0 e to the 6 would be the price of that bar. So dimensional analysis, it just helps you to keep track of the units you have, the units you're working with, and making sure you're canceling those units out correctly, you're setting up the calculation correctly. So in summary, the important things from today, right? Units in chemistry, the metric system, practice, converting those units and doing those calculations, dimensional analysis. And then lastly, the significant figures, right? That's really going to help us understand the importance of a measurement and where the error lies in that measurement, and that's going to help us in communicating a measurement to someone else.